Okay, welcome to our next section on measuring heat flow and specific heat. If you take a look at your unit organizer, this is the box section that we'll be covering about specific heat. And the questions you need to keep in mind are, what are the ways to measure heat changes? What are the units associated with heat and energy? How do you convert between calories and joules? And what is the specific heat equation, and what do each of the symbols stand for? Now, for this section, you do want a calculator handy in order to complete your notes. Okay, calorimetry is used to measure heat changes. I said in the last section, we can't really detect energy. We can really only detect changes in energy. And so calor means heat. So this is the measure of heat. So this is a very simple calorimeter here. Sometimes in lab we'll build a calorimeter and it'll just be a styrofoam cup and then with an insulating lid. So you've got a lid so that heat won't escape. And then you also have a thermometer, okay, to measure the changes in heat. So they can be very simple, they can also be very complex, and all you're doing is doing your chemical reactions within the calorimetry chamber, or the cup in this case, and you use the thermometer to measure changes in the energy. Now, units of heat. Heat has several different units that we can use. We have calories, with a little c, it's abbreviated CAL, okay, and a calorie is what's needed to raise 1 gram of water 1 degree Celsius, okay, so that's what defines a calorie. The calorie is the energy needed to raise 1 gram of water 1 degree Celsius. Now, it's not quite the same as a food calorie. This one here is a food calorie. It has a capital C. When it's abbreviated, it is CAL with a capital C. And like I was saying, this is your food calories. Okay, food calories. And 1 calorie with a capital C equals 1,000 calories with a small c, or 1 kilocalorie. Okay, because 1 calorie equals 1,000, or 1 kilocalorie equals 1,000 calories. So if we say 10 grams of sugar has 41 calories, you know, we read a label and it says that. Really what we mean is 10 grams of sugar releases 41 kilocalories of energy when it is completely burned. Now, calories are related to joules. Joules is the official unit of energy, and here is our conversion factor. 1 calorie equals 4.184 joules. Okay, so we can easily convert between calories and joules using that conversion factor. Now, fortunately for us, we don't have to memorize that number. Okay, if you take a look at the periodic table that we use here in class, you can see down here at the bottom, circled in red, is the calorie-joule conversion. So when you're doing these formulas, and I ask you to do this on a quiz or a test, all you need to do is flip over your periodic table and you'll see on the back the conversion factor between calories and joules. Okay, so let's work out a problem here, and I'm going to write the conversion factor. 1 calorie equals 4.184 joules, so I can see it for what we're doing here. So the question is, how many calories are in 19.2 joules? Well, we always set these up with what we know. Okay, we know 19.2 joules. And down here at the bottom always has to be the same units to cancel out. Well, do we know a conversion between calories and joules? Yes, we do. We have it right here. So since calories are what we're looking for, we set it right there on top. And then next to calories, okay, next to calories is a 1. So we write 1 calorie is equal to 4.184 joules. And we multiply the numbers on the top, we divide by the numbers on the bottom, and you get 4.5889. There's only 3 significant figures, so this should be 4.59 calories for our answer. Okay, so real simple conversions. If we want to do one going in the other direction, 2.5 calories. Underneath has to be the same units diagonal down so we can cancel out, and we're looking for joules. Okay, again, next to calories is a 1, and next to joules is 4.184. Okay, if you just look at that conversion factor, just put whatever number's next to it, and it's real easy then to determine whether you multiply or divide. Since it's on top, I'm going to multiply. I get 10.46 joules. Okay, only 2 significant figures. We look at that 4, it says round down, so it just becomes 10 decimal point joules for my answer. So 10 joules. So it's very simple, not a lot of heavy lifting on the math there. Now, heat capacity is a different concept. Okay, heat capacity is the amount of heat needed to raise the temperature of an object 1 degree Celsius. And heat capacity, we're just going to talk about it briefly, but it's dependent on 2 things. It's dependent on the mass of an object, and it's also dependent on the chemical composition. What is it made of? Okay, because the heat capacity of water is not going to be the same as the heat capacity of a piece of metal like gold. Okay, it also depends on how much you have. If you think about a spoonful versus a gallon of boiling water, which one would you rather have poured on you? A spoonful of boiling water or a gallon of boiling water? Well, most people would say a spoonful of boiling water because it has a smaller heat capacity than a gallon. Okay, so a smaller heat capacity for a spoonful of boiling water as opposed to a gallon of boiling water. So you can see it's mass dependent there. Now that's all well and good, but we usually want to compare the heat capacities of different objects. And so we get this term specific heat capacity. And specific heat capacity is the heat needed to raise 1 gram of a substance 1 degree Celsius. So now we're talking about a specific mass of a substance still being raised that 1 degree Celsius. And so since we're talking about the same amount, it's a lot easier to compare different chemicals and materials to one another because we're still talking about the same amount. The units for specific heat are joules over grams degrees Celsius. Occasionally, like in the chart on the right, you'll see joules over grams Kelvin, and it works the same way. We haven't really talked about Kelvin temperatures much, but we will more so in the next chapter. For this table here at the right, all of these are the same as saying joules over grams degrees Celsius, because right now Celsius and Kelvin are equivalent in these problems. So if you take a look at the table on the right, you have specific heats of common substances at a given temperature, and that temperature is considered to be room temperature. And if you look at the top of the chart, water has a very high specific heat compared to other things. So water has a specific heat of 4.18 joules per gram degree Celsius. But if you look at iron, which I've also circled down towards the bottom, it only has a specific heat of 0.449 joules per gram degree Celsius. And what this means is water is going to hold heat longer. It's a lot harder to heat up water than it is to heat up iron. If you think about holding some water in your hand and holding a piece of metal in your hand, the metal feels very cold at first, but then you can warm it up very quickly in your hand, as opposed to water. Or if you look underneath, water S, meaning solid water, ice, it takes a lot more energy to heat up that solid water than it does a piece of metal. And that's because they have different heat capacities. Now you have a very similar table in your book. It's table 11.2 and it's found on page 296. And so you're going to want to look at that to answer some of the questions for your assignments. So one of our calculations for this chapter is being able to do heat calculations. And the formula that we're going to be using is Q equals MC delta T. And Q here stands for heat. Occasionally you might see it referred to as a big Q, or sometimes you might see it referred to as delta H, which would mean the change in heat, because delta, the triangle, means change, and then the H standing for heat. Frequently though, it's a small q and it means heat. M is for mass, and it is going to be measured in grams. Oh, and I forgot to mention that heat is measured in joules. Okay, so heat's in joules, mass is in grams. C is the specific heat for a certain substance. So just like on that table on the last slide of the specific heats, that's what we would fill in there, is the specific heat for a compound from the table. And then this, of course, is measured in joules over grams, degrees Celsius, as I pointed out. And then delta T stands for the change, because of the delta sign, in temperature. And the way we get the change in temperature is we do the final temperature minus the initial temperature. And that's going to give us delta T when we work out problems. So you need to be familiar with all these symbols and what they mean. Now, in terms of memorizing the formula, again, if you refer back to the periodic table we give you, the formula is here, though written in a slightly different form. So on the back of the periodic table, no phase change for calorimetric formulas, no phase change. Q equals M delta T with a C sub P. Well, like I was just saying, the big Q is the same as the little q. And then that CP is the same as the specific heat capacity that we were talking about before. Okay, so they use slightly different symbols, but it's the same formula. And delta T, change in temperature, and M for mass. So let's work a couple of problems here. Okay, I'm going to write the formula up above. Q equals MC delta T. And so we've got a chunk of silver that has a mass of 15.2 grams, and a specific heat capacity of 0.2233 joules per grams degrees Celsius. If the sample is cooled from 100 degrees to 25 degrees, what's the heat released by the silver? So we've got Q, M, C, and delta T. What I find is easiest in these problems is just to make a list and find what you can. Okay, find what you can in the problem. So a chunk of silver weighs 15.2 grams. Well, that's our mass. 15.2 grams is our mass. It has a specific heat capacity given right there. Well, the symbol for specific heat is C. So we can fill in those units right there. The sample is cooled from 100 degrees to 25 degrees. So my final temperature is 25 degrees. My initial temperature is 100 degrees, so I get negative 75 degrees Celsius for my delta T. And the question asks, what is the heat released by the silver? So we are looking for Q. So we go ahead and plug things in our problems here. Q equals M. Here's my mass. C, my specific heat. And then my temperature. It's okay that you have a negative temperature. Okay, so negative 75 degrees Celsius. You multiply all those numbers together, and what you get is Q is equal to negative 265.62 joules. Because if you look, grams gets to cancel out and Celsius gets to cancel out. So I'm just left with Q, which is in joules. I only have two significant figures because of that 75 Celsius. There's only two sig figs. So this becomes Q equals negative 270 joules as the answer. Okay, this is where you can see Q has a negative number. So since Q has a negative number, this reaction is exothermic. And that makes sense because here in the problem it says the heat is released. When you have heat released and a negative Q, then you know it is an exothermic reaction. Let's do another problem that's different. Okay, now we have the temperature of a piece of copper with a mass of 95.4 grams increases from 25 degrees Celsius to 48 degrees Celsius when the metal absorbs 849 joules of heat. And the question is, what is the specific heat of copper? So again, make a list, see what we know. Okay, we're given a mass of 95.4 grams. The initial temperature, let's see, the final temperature is 48.0 degrees Celsius minus the initial temperature. Okay, gives us a temperature change of 23 degrees C. Okay. The metal absorbs 849 joules of heat. So heat is Q, so 849 joules. And the question asks for specific heat. So this time we're looking for C. So I've written the formula up above, but we're looking to solve for C. That means we need to get C by itself. So I want to divide by M delta T. And then here the M's will cancel out, and here the delta T's will cancel out, and I will be left with C is equal to Q over M delta T. So that's what I'm going to solve. So C equals Q, 849 joules, over M, 95.4 grams, over delta T, 23 degrees Celsius. Okay, and we take the 849, divide by 95.4, divide by 20, and you should get 0.3869, and some more numbers. But if we look back at that 23 degrees Celsius, we can only have two significant figures, so that becomes 0.39. And my units? Well, none of my units cancel out. I have joules, I have grams, I have degrees Celsius. So I just leave them the same. Joules over grams, degrees Celsius for my units. So this problem and the last one are the two most common things you'll be asked to solve for. You might see some where you're asked to solve for the mass or the temperature, but most times you'll be asked to solve for either Q or solve for C. So now as we wrap, you want to take a look at your unit organizer again, and take a look at the ways we can measure heat changes, our units associated with heat and energy, how we convert them, and then how do we solve specific heat equations and what are the symbols